asked in Slack. We will notify the speakers after 10 minutes, which means at this time you will have 2 minutes left. And we will do that by playing a sound and showing a sign like this. So you may either see or hear us. And to the listeners, it's nice to see each other, but when we are more than 100 people, this will affect the quality, unfortunately. So we ask you to put off your cameras while the speakers are speaking. And questions and comments, as we described in the intro mail, can be asked in Slack, in the Slack channel. This is how it looks for me. You will see in the top of this CIDER channel, there's a link to a Google Doc that explains how to do this. But basically, you just ask questions. For instance, if you have a question for Kirsten, you ask it in this thread. And if you have a question for Florian, the next one, you ask it in this thread. And the chair of each session will then pick questions from here and read them to the speaker, which can then answer, spending 3 minutes. And if there are more questions, this can be taken as in the thread, but after the talk. We have been maybe a bit ambitious with the program, so there isn't much time for each. So we ask you all the speakers to keep the time, please. Yes, and finally, we also have, actually at the moment only one, but maybe there will be more, recorded talks, which you can find here. Right, so the final thing is just to show the social organizing committee, the scientific organizing committee, which is Maria, Aswin, Christopher, and I. And it is only fair also to mention Stephen, who has been tremendously helpful and without whom this conference series wouldn't exist. I want to thank him particularly because he came up with the name CIDER, and I know he's very proud of that. So yes, I guess without further ado, I declare this workshop open, and let's go on to Kirsten. I think Aswin has a short introduction.
Welcome, everyone. I have the privilege to introduce Kirsten Knudsen today, who's going to kickstart this meeting by giving an overview talk about the observational aspect. So she's one of the leading experts in the study of high redshift galaxy formation and evolution using radio telescopes like ALMA, VLA, and the PTBI. So she received her PhD from the Stervat Leiden University, working with Professor Paul van der Werf, and went on to hold postdoc positions at Heidelberg and then at Bonn. She's now a faculty member at the Chalmers University of Technology since 2011 and is currently a Wallenberg Fellow and a scholar investigating the origin and fate of dust in early galaxies. Now I ask Kirsten to give the overview talk. Thank you.
Thank you very much for introducing me. Let me share my screen. And I hope you can see my slides. So, well, thank you for inviting me to actually give the introduction to this, to the CIDER meeting here, at least to the observational section of it. It's very exciting because looking into the Epoch Reionisation is the early phases of what's going on in galaxy evolution. And it's a very exciting topic. And I also have to say, I'm very much appreciating the whole organization behind running this meeting, because we are in difficult times, and it's getting the scientific exchange is essential for the progress. And therefore it's very nice that at least we're able to actually maintain this through all these online opportunities instead. So the focus is on the cold ISM, the cold interstellar medium during the Epoch Reionisation. And there's been immense effort going on in the past couple of decades in pushing this forward. And I have less than 25 minutes left by now, and I cannot do justice to all the different parts of it. So you will probably find that my introduction is a bit biased, but I try anyway to sort of go somewhat broad in this and give you some of the aspects that I think are important for understanding not just why we care about this, but also what are some of the effects that affects our understanding of what we're actually seeing in our observations. So just to set the stage, here's one of those famous nonlinear plots of the history of the universe, starting from the Big Bang and going up till today. And basically, even having almost 14 billion years of history of the universe, basically in a plot like this, the Epoch of Reionisation takes a very substantial part of the time displayed here. In fact, we're looking at a time that's less than 1 billion years after the Big Bang, so essentially beyond Redshift 6, if we're just talking strictly about the Epoch of Reionisation. But of course, one can draw this into a little bit the time that comes after this. So we start out from a universe today where we have more than 13 billion years of galaxy evolution, which started back from the time of the Big Bang, and shortly after the Big Bang, at the time of the recombination, we got basically hydrogen and helium, a little bit of lithium. We didn't have all the elements that we see today. They have come through the processing that the nuclear synthesis in the stars that has been growing, or the stellar mass that's been growing in the galaxies that we're seeing. And of course, we also got the cosmic macro background radiation, which of course affects us and affects what we're actually seeing in the high redshift universe. Now, the first stars and galaxies probably started somewhere around maybe 200 or 300 million years after the Big Bang, with the early formation of these. However, this is a topic on its own, and I know there's been a previous meeting on this. So I think if you're interested, you might actually be able to go back and find some of the recordings of this. But if you now move further on, trying to actually see how far are we actually seeing, how distant are we seeing, and some of the most distant candidates we have now are out to about Redshift 11, unless I missed that, maybe something new came up more recently. And so we're pushing the frontier of what we're able to see, and we're doing this both by looking at galaxies of various types, but also not just strictly galaxies, but also looking for quasars and AGNs. And of course, the brighter the object, the easier it is to see it far away. But there's also other effects that actually that I will cover a bit as I talk about how far we're actually able to see. Let's see. So if we think about galaxies, galaxies are stars, gas, dark matter, etc. And they're not closed systems. They have an interaction with the surroundings. And so one of the questions is, why do we care about the cold ISM, and why do we do this during the Epoch of Reionisation? Well, the stars we're seeing in the early galaxies, of course, formed out of the gas that is around them. And of course, the gas has to be in a state and have conditions where you can actually do star formation. In the stars, we have the nuclear synthesis. We have a return of matter to the interstellar medium. But the interstellar medium, of course, as I said, galaxies are not closed boxes. There is an inflow of gas that comes from the circumgalactic and the intergalactic medium, but we also have outflows. We have return of gas back out of the galaxy. So we have a feedback process that takes place as well. And of course, the Epoch of Reionisation is the time where the intergalactic medium goes through this phase transition of having been neutral to being ionized. That means we also need to have photons escaping from these early galaxies. And so ultraviolet photons need to reach from the galaxies, from the young stars and AGN, out in all the way out of the galaxies. And that, of course, is very affected by what is happening in the interstellar medium. For example, dust obscuration could play a major role here. So why do we care about the cold interstellar medium? Well, this is the fuel for the star formation. It's also the fuel for the growth of supermassive black holes. It is, the interstellar medium represents basically the recycled dump of galaxies. So it's because maybe we have stars are formed, they die, they return their matter, new stars are formed, etc. And of course, this is also how the gas that's been enriched with like increasing metallicity gets not just redistributed within the galaxies, but also gets removed out of the galaxies. And so we also experience this in an outflow. We have the feedback processes. So the ISM is also a really good probe for what are the heating processes and the cooling processes. And for example, we can use this to get an estimate of what is the UV radiation that is coming from the young stars. And again, I emphasize for the Epoch of Reionisation, this is really important because we want to understand how does the UV escape. So from an observational point of view, we can use the gas observations to understand and probe a lot of different things. One of them are the kinematics, so like how the gas is moving about. But it could also be the excitation conditions. We can measure the masses of the molecular gas, the atomic gas, of the dust, etc. And so it gives us an idea of what is the current state of each of the galaxies we might be looking at. On the other hand, specifically ISM in the Epoch of Reionisation, as I said before, we want to understand, for example, the impact of the UV radiation so that we have the coupling out of the galaxies. But it also represents really the early stages of galaxy formation. So basically, this is where we lay the foundation for everything we see in the coming 13 billion years. And again, as I said, for the enrichment of the circumgalactic and intergalactic medium. So it's also really important that we understand in this epoch, how do we translate between our observational results and the physical properties, because this might not necessarily be exactly the same formalism that we're using as we would be using in the local universe. Some of the relations that we find from the local universe galaxies might not hold for the high redshift universe. Some of that, like in principle, physics is the same, but it might be that the conditions is such that galaxies will appear differently. So I'm gonna, there's been a lot of results coming out, and I'm just gonna pick some different ones to sort of showcase a little bit about the different progress that's been. And so here I'm just showing just one of the very first results that came out of dust and gas detection beyond redshift 6. And so this is from the Sloan quasar J1148, which was a redshift 6.4, which was one of the first dust detections of that in that epoch. This was, of course, this is a quasar. It was very, very bright. It's a very massive system, and let alone finding such massive supermassive black holes at that early epoch is quite spectacular, and it's very spectacular. I know there's been yet another meeting also on quasars during the ER. So I won't go into the details about that, but I just want to highlight here that finding dust masses that are equivalent or similar, even higher than what we find in, for example, the Milky Way is quite important. And so already in 2003 and 4, finding a little bit against what were the initial predictions or maybe expectations, whether it should be possible to find so much dust at that time, there was actually detections, and again, more detections have come afterwards. So of course, it's very easy to start on the bright end, looking at quasars and looking at extreme starburst and seeing that something is happening. But of course, we want to understand what's going on much more generally for all kinds of galaxies. And so I've been doing ghostly galaxies for many years now. And one of the things that makes it actually, I think, quite fun, particularly interesting also about looking for dusty galaxies is that this particular feature that we call the negative K correction. And so this is what I want to illustrate here is actually taking a slide taken from, or a figure taken from a recent review by Jackie Hutch and Elizabeth de Cunha, where the point I want to make here is that if you take an SED, this is a model SED they've done, it's been redshifted between redshift 0.1 and up to 10. And if you look here in the range that is the submillimeter and millimeter part, you'll see that even having a galaxy SED for the same luminosity, just by redshifting it and going up the radiation slope, effectively have the same flux density measurements for the same luminosity in this range. And it means that if dust-rich galaxies exist at high redshift, very even into the ER, we will actually be able to see them. Simply just because it's not just that they are farther away and therefore fainter, we actually have a little bit of help from the SED shape. And there's been numerous surveys doing this. And one of the very recent ones I'd like to highlight here is the 2 millimeter survey, the Mora survey from Zavala and Casey et al., where by pushing in to really high redshift and doing more systematic observations, it's actually possible to both get detections, but also put constraints on what is the relative contribution between the unobscured star formation and the dust-obscured star formation. And so based on this survey, which this is still probing the brighter end, but it gives a very good indication. The plot here has the relative contribution by the obscured and unobscured star formation, both in the middle panel but also the lower panel, which shows the cosmic star formation history. And you can see as you're going to higher redshift, the unobscured star formation play a relatively larger role. And this, of course, has been a very big discussion for the past 2 decades of actually trying to understand how much are we seeing when we probe up from the from the optical UV observations versus how much do we get from looking in the dust observations. And so now, of course, what remains here is filling this up with deeper surveys and getting a more complete picture across the luminosity range. Now, another really important aspect that I also mentioned before is the cosmic microwave background radiation, because today we have a CMB temperature around 2.7 kelvins, but of course this scales with 1 plus the redshift, and so beyond redshift 6, the CMB temperature is larger than 20 Kelvin. Now, this is the moment where most of you will be thinking that's still not, doesn't feel very high, but if you look at the cold interstellar medium where we have temperatures, say about 20 Kelvin, 40 Kelvin, 60 Kelvin, etc., this actually becomes a significant heating contribution. And so this can be a significant effect. It will not always be a significant effect, but it is not something that could be neglected when we talk about the epoch of reionization. There's a number of sorry about that. There's a number of papers talking about this, and one of the very important ones is from de Cunha et al. Has done extensive modeling on this and also developed a framework that is very often being used for correcting for the or taking into account the CMB heating. And so I was taking a couple of plots from that paper to sort of highlight the effects that the CMB can have, again, said on this framework that she developed. And on the left side, you have here a dust component which has a temperature around 18 Kelvin. But if you go beyond redshift 6, you can see that the CMB actually contributes with heating, and therefore the actual temperature of the dust component will be larger. Now, what does this mean in terms of observations? Is taking a similar type of thing here is on this is an SID that's set and including the effect of the CMB. So the gray one here is just the intrinsic SID modified black body without the effect of the CMB. Now, including heating from the CMB, it would be more like the black line here. But of course, when we observe it, we're seeing it in contrast. We have to see it as a contrast up against the CMB background. And therefore, again, it will look different from what it in fact is. And this is reflected in the dashed line here. So dust observations and the epoch of reionization will, depending on the intrinsic temperature, will be affected to some degree by CMB heating, and therefore observations will be affected by this. The colored lines that are here in the vertical lines reflect the different ALMA bands. Now, it's not just the dust, it's also the CO observations, or basically some of the molecular lines that are affected. But CO, since this is one of the most common lines for extragalactic people to trace the molecular gas, of taking one of the figures from that paper to illustrate this. And again, if we have a component with different kinetic temperatures here with the blue, red, and yellow, highlighted here, then the different going to progressively higher redshift will affect how we see the line SED for these sources. In this case, it's the LTE case. If one takes the non-LTE case, it becomes even more complex. But they're just a kind reminder that CMB plays a role both in what happens in the ISM, but it also plays a role how we interpret our data. Now, dust detections happen, I showed before, there was one of the quasars, one of the first ones, but they're coming in gradually a bit at a time. And here I have just a very small compilation. There are several more detections in the literature, but showing both from the right side where I've put the quasars and AGNs as some example, in the middle having brighter galaxies, starburst-like sources. And then to the left side, I put lens galaxies to illustrate the low mass and the low star formation rate systems. And those, again, typically need to go through the lensing to actually probe these. And what's quite remarkable is that we're actually finding dust masses that are like 10 to the 7 solar masses or more. And again, I just remind this is basically equivalent to what we have in our own Milky Way. But a lot of effort is going into understanding where does this dust come from, how does it survive in this environment, or how does it get reprocessed, how do the dust grains grow, etc. And there's a lot of funding being rewarded to this at the moment. Several places, I can see several groups have been posting positions at the moment because to actually study this. And so we're seeing more and more dust. That's exciting. But I think there's another aspect which is equally exciting, is that we're seeing a large number of non-detections for dust. And part of this, of course, reflects maybe the depth to which we're actually having like the sensitivity of the observations. but it also reflects that there's probably something we don't understand about dust. It's either because the metallicity is lower and therefore there will be less material available for actually making the dust grains and growing them. But it could also reflect that there are other aspects that we haven't understood about the physical conditions or the properties of the gas. And one of these could be that, and this is just an example I took from the literature from Feistadel, is that the temperature might be different. Of course, this is very difficult to determine just sort of from one or two photometric data points. So it could be that we are there because we don't have enough data to make these constraints, but it could also be that the physics actually such that the temperature will be significantly higher because of the early stages of the galaxy formation or galaxy evolution. So what I want to highlight with this plot is that given the big error bars that are here trying to actually make the estimate on what are the dust temperature and how to best to characterize the dust SEDs, is very difficult, and therefore this is not a settled topic, but it's opening up another big set of questions. So I think in the next 5 years, when samples will be growing, we'll also be getting a much better handle on this. And this, of course, is essential input towards what's happening on the modeling side as well. But of course, dust is mostly something we observe in the continuum, and I have to admit here as well that what I'm showing, we studied the ISM across the whole electromagnetic spectrum, in particular in the optical infrared, millimeter and into the radio, but my view here, what I'm presenting, and the last part of my talk was very biased towards the far infrared and millimeter part. So it's not that I've forgotten that we can see the ISM across the whole spectrum, it's just that we're limited in time, and I think what a lot of the progress that's been happening over the past few years has actually been the delivery of data from ALMA and other millimeter observatories. So looking at the spectra, we can actually look at different spectral lines, and this really opens up opportunities of seeing details that we otherwise wouldn't be seeing. There's a lot of different spectral lines. Carbon monoxide CO has been probably like the most common tracer. I said that before as well. And here's a plot that I took from Carilli and Walter review from 2013. I forgot to put in the reference. I apologize for that. But what you're seeing here is the different CO transitions, different transitions, as they're being redshifted through the different bands. And here's the ALMA bands, it's the VLA bands. I put ALMA here and VLA just to help indicate. And you can see that when we get out beyond redshift 6 or just to high redshift, it's basically just the high J transitions we're seeing with ALMA. So if we have to see the low J transitions, we have to go to the VLA. And of course, keeping in mind that the low J transitions have excitation temperatures comparable to that of the CMB, that of course is also significantly challenged. So that can be very difficult. We also have another part of the spectrum, which is very exciting, which is the fine structural lines that are seen in the far infrared. So these are atomic lines from neutral and ionized gas. And there again, similar kind of plot, we see how the transitions redshift out through that gets redshifted through the different bands. Here are the ALMA bands and here the VLA bands. Below here is more the dense gas tracers like HCN and HO+, but I like to focus at the top with the fine infrastructure lines here. And so one of the ones that have been discussed a lot is using carbon plus, so ionized carbon as a probe for a lot of things. And the reason for this is that it is one of the brightest cooling lines we see in local star forming galaxies. And that, of course, can be used as a tracer of various aspects of what's happening. And of course, we're also interested in getting, for example, the carbon-1 line. And if you can get a combination of these, is maybe a good probe for finding the total molecular gas mass. And I think this will also be discussed in one of the future talks here. Of course, if one can get the combination of all these lines, we can do a lot more. So here's a figure just to illustrate this that I've taken from the very recent paper by Matten et al. And I want to use this one just as a way in to illustrate, for example, the uses of carbon plus or C2 observations, but also again reminding you that it's particularly if we have low metallicity environments, the situation could be remarkably different from what we see in just normal metallicity environments. And so what the illustration has here are like bright stars in the middle, the young stars as a UV radiation field. And molecular cloud, where we very often would assume that the carbon monoxide will be tracing the H2 gas quite well. But if you have a low metallicity environment, this is probably not the case. There might only be a limited amount of CO, but there will still be a big reservoir of H2 And therefore, actually, the atomic carbon might be the better way to trace this. So just taken from the local universe literature, here are a couple of examples showing how the carbon plus in comparison to a number of other traces, for example, the far infrared emission, or using other traces for looking at the star formation rate, actually finding that there is a good correlation or some kind of clear relation between star formation rate and line luminosity. And this goes both for the carbon plus, but also for some of the other far infrastructure lines, far infrared, far structure lines. So it was suggested that carbon plus will basically be one of the best tools for us to understand galaxies in the EOR, because it's redshifted. The line is redshifted into the millimeter band, so it's very easy to observe from the ground. And there have been a couple of, there had at that point also been a few different detections, but still limited to very few sources. So in 2015, Epoch et al. Published a paper with results from Redshift 5 to 6. This was the first bigger sample with 10 sources, all with carbon plus detections, and some of them also with continuum data. And stepping on from there, but the number of detections has been growing. Again, most of them are individual sources. Most publications have 1, 2, or 3 detections each. But this is slowly growing into becoming more systematic surveys. And I note that there are actually very big surveys that are coming out now, in particular from the ALMA large programs. So from Alpine, which I think there will be a little bit more about later, the ALMA Lantern cluster survey, which is also represented here. And then there's the Rebels as well. And the difference is a little bit the redshift range, but also the parameter space that's being probed, because the Lantern clusters will probe the somewhat lower mass and lower star formation rate range, while the galaxies that are individual fields will be probing, they're not typically not lensed, and therefore be probing sort of the slightly brighter end. Now, comparing the line luminosity of carbon plus to the star formation rate, plotted up, this is a diagram from Alexandra et al. There is lots of these diagrams in the literature. Comparing the local relations from Deloes et al., it's seen that on the brighter end, things sort of compare well between the high redshift and local high redshift universe and low redshift universe. But if we go to the lower part of the parameter space with the lower star formation rate, we're actually seeing that the galaxies tend to be underluminous in their line luminosity. And so this has been a really important result. And there's a major effort also on the modeling side going into actually understanding how well can we use, like, what does this actually tell us? So it's not quite straightforward with the interpretation of this, but I think this is opening up is a really important aspect of understanding the early stages of galaxy evolution, at least the conditions of what's happening in the heating and cooling processes of the ISM, but also the effect of, for example, metallicity. So this is where we're going to see a lot of progress in the next 2 years. But
two
yes,
minutes left.
Thank you. So going from the carbon plus into the other traces, we have the oxygen 3, for example, and this is also where, again, there are no major systematic surveys on this. I expect 5 years from now, giving this in talk, we'll have major systematic surveys on this, but it's very difficult because, again, we need a lot of observing time for a lot of sources. But it's coming, it's growing there. There's a few examples that I want to highlight here. But again, having single line studies versus not as much single source, but single line studies is nice, but it's more fun if you can put them together. And so here, just to make an example from the Alexandra et al. Paper, they put the line ratios, luminosity ratios here, and you can sort of see a tendency that the galaxies tend at the early part, sorry, that was my own timer, that the luminosity, the oxygen 3 tend to be brighter while the carbon plus tend to be fainter. And of course, this can possibly be explained by trying to understand how different physical effects go. This could be the distribution of the gas, it could be the metallicity, it could be the ionization fields, etc. When I say ionization field, I mean like the UV radiation field as well. So I'm not actually supposed to talk about models, but I did want to put in one of the models from Katz et al. For simulating a number of galaxies. Here's an example for a single galaxy in the simulations, show how different traces, so different transitions, here's the oxygen, the carbons over here, oxygen, neutral oxygen, nitrogen, etc. How for the same galaxy, in the process, like this is of course process simulations, they look somewhat different, not fully different, but we'll be probing different parts of it. Some of it's probing the ionized gas, some of the neutral gas, some of the molecular gas. And therefore, we need to, the next really big step in order to make a significant progress in the next few years is actually getting this multi-transition studies as well. And there was very recently, just a couple of days ago in the literature, there was a Redshift 4.7 result that came out for BR1202, one of the big quasars that also has companion sources. There was oxygen 1 results as well, which I thought was quite nice to see that, like, again, it's small steps, but this will actually at some point become much more systematic studies. And I think so it's like there's this really cool future ahead of us and how much we can do. So I'm just in the last 30 seconds or minutes, whatever I have, is talking about a little bit what are some of the big challenges we have for understanding early galaxies. And it's of course also from the observational point of view, is that we have very short timescales, like compared to looking at galaxies today. But we also we don't know very well the star formation history and the initial mass function of what happens in the early phases of the galaxy evolution. We don't know how the
time is up.
Yes, okay. So metallicity enrichment is very important, and also affects the dust production, which we'll hear more about later as well. And then the UV radiation field. So we're basically the connection between what happens in the small scales and the large scales. So I put up my summary, just reminding you that we have an increasing number of gas and dust detections. We have major challenges in understanding what's going on, which I think is pretty cool, because it means that there is more opportunities for more stuff to learn. And then we have in the outlook, we have a really bright future, because we're now getting enough single studies that will help us define and actually understand better how to move ahead in major systematic studies. And of course, with ALMA, the JWST, ELT, and SKA, I think we'll actually have the next 5-10 years will yield a very good understanding between the link between galaxy formation and the EOR. And of course, tomorrow will the modeling be really important. So I'll stop.
Thank you, Kirsten. I think we don't have any time for questions.
If they're in the Slack, I'll look at the Slack channel. So.
Yeah, maybe we can actually do one question by Ilsung Yoon. How much do we understand the impact of cosmic ray in the EOR?
I think that's an excellent question, and I don't think this has been studied quite as extensively as has been studied at slightly lower redshift. So I think this is a very important aspect to bring. I would actually ask the same question once more to the people who do the simulations. I think that's a very good point.
Oh, thank you. There's one more question in the Slack. I guess you can ask it there. And thank you again.
Yes, thank you.
I think we have like a 5-minute break now.
Yes, let's have a few minutes break. Or yeah, we could maybe even ask the question. Let's have a few minutes break and stick to the plan, and we'll go on with the first session.
Peter, maybe during the break, do you mind reminding some of us who are computer illiterate how to find the questions in the Slack?
Yes. Oh, no, I wouldn't. So you let me just show this again, actually. Yes. So you see on Slack, you have the CIDER. And if you go to almost to the top, there's a pinned message, which is sort of yellow. And just below that, we have a thread for each talk. So this is the first one by Kirsten. And you see the questions are here. So the next talk, which will be by Florian, you will just ask question in this thread. So you type questions here. And I will be chairing the next session, so I will pick questions from whatever questions comes here, and the ones that Florian doesn't have time to answer, she can answer in the chat. So each question will belong to a certain thread. Does that make sense?
Yeah, perfect. Thank you. I had not looked toward the top for the pinned section. That makes sense. Thank you.
Sure.
I think it's perhaps worth just emphasizing as well, if you have further questions, you know, that you think of later after the talk, then feel free to put those in the thread, and the speaker will be able to follow them up during the workshop as well.
So while we're waiting for the next session, I just want to thank you, Kirsten. I think it was a really excellent talk. I understood a lot, despite not being an observer.
Oh, I hope so. I think it's a very exciting epoch as well. I see there's a couple of questions. I'm trying to answer those.
Yes, go ahead.
But I actually think really like there's going to be a lot happening in the next few years, because the trick is to actually get the observing time on the big facilities. But I think what we need is a little bit more talk between the observers and the people who do the modeling.
Yes, I agree. Right, with 1 minute left to the first contributor talk, let me introduce this. So we actually tried to make 4 different sessions and group the talks together, but in the end, it was more or less arbitrary. But the first couple of talks have to do with Lyman alpha, which is my favorite wavelength, and the first one will be by Florian Leclerc, whom I had the pleasure to go skiing with in Utah a few years ago. And she's from Geneva, working at Geneva, and will tell us about the cold interstellar medium, circumgalactic medium at high redshift observed in Lyman alpha. And you already, I think, yes, you already shared your screen. So, it's now time.
Okay.
Please start.
So first of all, I would like to thank the organizer for allowing me to give this talk. And so I'm a postdoc at the University of Geneva, and I'm also working within the MUSE collaboration. And so today I want to tell you about the cold ISM and CGM of distant galaxies observed in Lyman alpha. So just a bit of introduction, talk about the circumgalactic medium. So why do we care about it? Because this is really where we expect the gas exchanges between the galaxy and its environment to take place. And those gas exchanges are really regulating the star formation. So if we want to know more about the galaxy evolution, we need to observe this circumgalactic medium, and to map it, it's quite difficult because of the low surface brightness of it. And so to map the cold CGM, we can use the Lyman alpha line, which is the brightest line, recombination line of the hydrogen atom. And it's also a resonant line, meaning that it scatters and illuminates the H1 cloud. And here on the left, you can see those Lyman alpha extended emissions, so scattering into the CGM for at low redshift in blue. And at high redshift, we can see also those big and bright nebula, Lyman alpha nebula and blobs around the quasar and massive galaxies, but of course they are not representative of the bulk of the galaxy populations. So what we would like to do is observe the cold ISM CGM for low mass galaxies, and for that we need sensitive instruments. And this is what we are trying to do with the MUSE, which is an IFU. And all the results I'm going to present you here are based on data from the Muse Deep GTO program, targeting the Muse Hubble Ultra Deep Field. And so those Muse data are 10 to 30 hours deep, and it is a mosaic of 3x3 Muse fields. And here you see the redshift distributions, and you can see that at higher redshift higher than 3, we see only Lyman alpha emitters, and we have actually about 800 of Lyman alpha emitters. And so around those objects, we try to detect extended Lyman alpha emission to trace and characterize cold circumgalactic media. And actually, we did found quite a lot, so more than 140 Lyman alpha halos. And here, I don't want to give you too much details about the spatial analysis of those Lyman alpha halos. I just want to say that they appear to be ubiquitous around galaxies at redshift higher than 3, which underline the fact that the CGM has a rich cold gas content at high redshift. And those halos extend over tens of kiloparsec. They are also, their properties do not evolve much between 3 and 6, and they appear quite diverse. And also, it's quite difficult to link the properties of those Lyman alpha halos with the UV properties of the host galaxy. So linking ISM and CGM properties is quite difficult with Lyman alpha. So what about the spectral properties now? So as I told you, the Lyman alpha special Lyman alpha emission looks quite diverse, but also the Lyman alpha lines look quite diverse in shape. And so our new study, let's say, is to study the spectral properties of those Lyman alpha halos. So we start from this parent sample of the halos we have from Muse, and for the 6 brightest ones, we were able to carry out a resolved analysis. And for the others, we just tried a 3D decomposition of the ISM and CGM contribution of the Lyman alpha. So here you can see the distribution in properties of our sample. So with this selection, we are selected the brightest galaxies in UV and in Lyman alpha, but still those are quite low mass galaxies, so 10 to the 9 solar masses on average. And so here I'm starting with the resolved analysis of those halos. So on the left, you can see the HST image. So tracing the UV continuum of this galaxy, for instance. And here, this is the corresponding Lyman alpha narrowband image. And what we've done is we perform Voronoi binning. So in the solid contour shows the area studied for this resolved analysis. So this is only the inner part of the Lyman alpha halos. So it's in 15 kiloparsecs. And we fit the Lyman alpha line in all the different bins. And this is so we got some map. So here I'm showing the map of the peak shift of the Lyman alpha line relative to the line in the center, because we don't have the systemic redshift for those galaxies. We only have Lyman alpha line, which is a resonant line, so it doesn't trace the systemic redshift. And here, this is a map of the width of the line. And here I'm showing some lines extracted in the center in orange and in the different region of the CGM in blue. So yeah, in the center, we can say that it's the ISM, but it's not resolved in this case. Okay, so as I told you, there is 6 objects like this. So here I'm showing 2 more. And what we can see is that there are variations in the Lyman alpha line shape. Those variations in the peak position, for instance, are quite small, so lower than 200 kilometers per second, but still significant. They are a bit larger in terms of width of the line because they go up to 500 kilometers per second. And we see that the lines varies between the ISM part in here and the CGM part, but also within the CGM itself. For instance, here the lines are different and here also. So it means that it suggests that we have a complex and diverse configuration of the H1 distributions for those galaxies. What we can tell also is that we do not observe an obvious velocity fields, except maybe for these objects here, and also maybe this one. And this would suggest that we have a CGM scale bulk rotations. And I refer to Smith et al. 2019 for this, because it observes this in simulation as well. And also in all the bins, we have single peak Lyman alpha lines, except for this object in this bin, where we have a kind of blue bump, which would suggest that there is an infalling gas here, so which is interesting as well. Okay, so this is for the resolved analysis of those Lyman alpha halos. And now I want to talk about this 3D decomposition of the Lyman alpha halos. So for this, we were able to increase the sample, but we have to ask a simpler question, which is, are the Lyman alpha lines emerging from the ISM and the CGM the same? Are they different? So I won't go too much into the details about the decomposition, but it's 3D two components models, and which enable us to really disentangle the line from the ISM, emerging from the ISM and from the CGM. And yeah, so with this sample of 19 objects, we were kind of able to carry out a statistical study. Okay, so if we look at the distribution of the full width SF maximum in the core or ISM in orange and in the halo CGM in blue, we can see that the lines appear to be in median. So if we look at the vertical lines, broader in the CGM, and also redder. So this configuration is expected if the Lyman alpha photons are emitted in the ISM and then scattered into the CGM, according relative transfer models. And it could maybe tell us a bit about the origin of those Lyman alpha halo, the powering mechanisms. Now, if we look on a galaxy by galaxy basis, so we look at the ratio between the two for each galaxy, and the peak separation between the two lines in the ISM and the CGM, we see that those distributions are quite have a large dispersions, quite wide. And so this indicates that we, again, meet different configurations for the called ISM CGM traced by Lyman alpha. For instance, the line can be narrower in the halo than in the core, but also bluer. So we really find a large diversity. And now that we have those parameters, we looked for correlations. So one of the correlation we found, so we found only two, but one of them is this one. So the peak separations, the peak shift of the Lyman alpha line in the halo compared to the width of the halo, and we see that.
So that's 2 minutes left.
It correlates, and this trend is also observed in integrated spectra. So this is a paper by Vera et al. 2018, and they also this is quite well explained by expanding wind models, meaning that again the photon would be emitted in the center of the galaxy and then scatter in outflowing media. And which is interesting here is that we actually also see this trend locally in the galaxy. So this would mean that we are really seeing outflowing gas at different scale. And also, as we saw earlier, with variation in the H1 column density, so could be maybe some clumpy outflows that we cannot resolve the clumps with the Muse data. Okay, the other correlation that we found is the width of the lines, both in the ISM and CGM, with the beta slope. So meaning that the radio galaxies show a broader Lyman alpha lines, both in the ISM and CGM, meaning that maybe the more evolved galaxies will show broader lines. So, so this was the second correlation, and we didn't find any other correlation. And also, as I showed you, we found a large diversity of the Lyman alpha lines. So meaning that to really understand this connection between ISM and CGM, at least with Lyman alpha, because we need to decode the line, we really need models and simulations. And this is actually an effort which is ongoing. So here I'm citing some studies. some recent studies. And also to decode this line for those high redshift objects, we need the systemic redshift to better characterize kinematics, for instance. And this would be possible with, for instance, James Webb Space Telescope or other instruments. And also, if we go deeper in the data, maybe we can detect other lines like C3. And this is what we are investigating in the Muse extremely deep field, which is 140 hours deep. And also, yeah, we would like to have better spatial resolutions to resolve the ISM. And the lensing can greatly help here. And I'm referring to this paper where we study 2 Lyman alpha halos, so lensed Lyman alpha halos. And also we can use adaptive optics with Muse. And this is my summary slide. So I just presented you the first analysis, statistical analysis of the spatially resolved spectral properties of the Lyman alpha halos around the high redshift galaxies. And the main conclusion is that maybe this study suggests that we are seeing outflows at the ISM and CGM scales. And it also underlines that it's difficult to connect the cold ISM and CGM, at least with Lyman alpha. And that we will need model simulations or maybe the help of lensing to improve our understanding. And thank you.
Thanks a lot. Thanks a lot. That is excellent. Almost on time, and we have plenty of questions. I think we have time to answer one of these. I will let me just see here. I'll take the first one by Ilseng Yun, who's asking if these Lyman alpha emitters are in overdense regions, so like proto-galaxies.
No, so the UDF is quite is not an overdense region, so I would say no. And we also have, we are finding Lyman alpha halos from redshift 3 to 6, and they are quite well distributed. So I would say no. Okay.
I guess there's time for a quick question. So you define how do you define the border between the galaxy and the halo? When you say 65% of the flux is in the halo, how do you observationally define what is halo and what is galaxy?
So we are fitting so the UV scalens is fitted on the HST data, this HST image, so without Lyman alpha. And we are using this scalens, we fix this scalens, and then we use our 2 components model where the scalens of the first component is fixed to this HST UV image. And this is what we call our core or ISM component.
Cool. Okay, thanks a lot. There are more questions for you to answer in the chat. But let's move on to the next speaker, who is Alexandra Rust from Stockholm, who's telling us about spatially resolved comparison of Lyman alpha and atomic hydrogen emission in low redshift, high redshift analog galaxies. You are here, right, Alexandra? Yes.
Hey, yes, can you hear me?
Yes, indeed. And I will start the time now.
Okay. Can you see my screen?
We can. But now I think you muted yourself.
Can you hear me again?
Yes, now we can hear you.
Okay, so I'm Alexandra Rust. I'm a PhD student at Stockholm University, and I'm going to tell you about a work that I did with the last team on the first spatially resolved comparison of Lyman alpha and 21 centimeter H1 emission in galaxies that are analog to the one at high redshift. So the talk is going to go like this. I'm going to start with a short introduction, just stating the questions that motivated this study. I will show a bit more about the sample. I'll present the H1 observation and the multi-wavelength analysis showing the Lyman alpha and the other components of the interstellar medium. And I will finish with a brief conclusion. So Lyman alpha is a key probe of galaxies at high redshift. And it's essentially, I'm not sure everyone is familiar with it, so I'll just give a bit more of the basic. It's the transition between the first excited state of the hydrogen atom and the ground state. And it's a resonant line, which means that it's captured by the hydrogen, and it's also absorbed by dust. So the photon transfer in the interstellar medium should be mainly impacted by the dust and the H1 content, but also distribution. And so in order to use Lyman alpha at galaxies in the epoch of reionization, we need to understand how Lyman alpha transfer proceeds in galaxies and how the multi-phase interstellar medium impacts it. So the thing is that we can't really get good result of the observation of H1 and of the 21 centimeter emission, which is the best tracer of the H1 at high redshift. So the observations of local galaxies are the only way to get a precise view of how the Lyman emission is impacted by different phases of the ISM. And so that's exactly what the Lyman alpha reference sample has been created. So the LAS and ELAS sample are made of 42 nearby, and when I say nearby, it's very nearby for people in the audience at redshift of 0.03. And they're star-forming galaxies, and they were selected on H-alpha equivalent width and FUV luminosity criteria to resemble Lyman break galaxies. And you can see on the bottom the BPT diagram on the left and the main sequence on the right, with the galaxies in the sample that are overlaid. Now, we didn't use the full LAS sample to do this study because H1 observations are quite hard to get at the resolutions we wanted. So we observed two galaxies, which are LAS 8 and ELAS 1, or NGC 6090. They are quite massive. They have stellar masses around 10 to the 11 solar masses and quite metallic as well. So they're very different from what you would see at high redshift. And you can see some nice HST color images on the bottom of those two galaxies. And the Lyman alpha is the fuzzy blue that you can see there. And so these galaxies were selected mainly for their very high H1 luminosity, which would allow us to do those high angular resolution observations. And now if you want to compare it to the diagram I showed you before, this is the position of the two galaxies on the main sequence. And so we went and got some very large array observations of the 21 centimeter line for those two galaxies. And so we observed the two galaxies using all the different array configurations from the more compact, that is more sensitive to large scale emission, to the more extended baselines, which have a good angular resolution. And we got 50-hour observations per galaxy. And with that, we were able to make a final H1 data queue by combining data from all the array, reaching a 3 arcsecond resolution in H1, which is roughly 2 kiloparsec physical resolution at those redshift. And this is what we see. So on the top panel, you can see LAS 8 H1 moment map, and on the bottom panel, this is ELAS 1. From the left to the right, you have the column density map, the weighted velocity map in the reference frame, and the standard deviation map for the velocity. And we get a mass of roughly 10 to the 10 solar masses for the H1 in both systems. And so if you want to compare to the HST image that I showed previously, this is the HST field, which is 40 arcsecond that is overlaid on the images. And the images that I showed in previous slide is really at the center of that. So that really shows how extended the H1 is. And on both, in both those galaxies, we can actually see signs of interaction. In LAS 8, you have a small companion galaxies that is to the west, the southwest of the galaxy. And in LAS 1, you have very extended tidal tails of H1. Now, the most interesting part, I guess, is so the comparison with different phases of the ISM. So if we look at the H alpha and the H1, this is the figure on the left. where you can see the moment map that I showed previously with the H alpha emission from Muse overlaid. And you can see that there are there is star formation going on along the spiral arm, but also, and most importantly, very strong star formation in the center. And to the right, you have the extinction map that is computed using the H alpha over H beta ratio. And essentially, the lighter colors show you lower dust content, while the darker colors show you more dust in the galaxy. And so there is really this divide in the galaxy between the west and the east, and we'll see that's quite important. So the western part of the galaxy has much less dust than the rest of it. Now, if we look at the Lyman alpha and the H1, and this is the first time we can see that at those resolutions, we see that the Lyman alpha essentially is located to the west. This is also the place where there is lower dust extinction, so it's quite interesting. And it's nearby the more high column density H1 contours, but it's still not overlapping with the high H1 column density. And then if you look to the right, this is Lyman alpha overlapped on the moment 1 map, and it is coincident with the blue shifted side of the H1 disk. Now this is interesting, but I think the more interesting part is the 3D analysis, because we can do that with an H1 cube. And so the top panel shows the Lyman alpha versus the H1 spectrum. Lyman alpha is the very dark blue line, and H1 is the lighter blue line. And they're both extracted in the same small 3 arcsecond aperture that is there. And what you can see is that there is a redshift of the Lyman alpha line and a blue shift of the H1 compared to 0 velocity, which could explain why Lyman alpha photons can escape easily in the galaxy. And on the bottom panel, you have another way to see that, is to say the H1 channel maps overlapped on the H1 image. And so from left, you go to the blue shifted side to the more red shifted side. And what you can see is that really when you look at the most red shifted part of the H1 disk, you don't have H1 in front of the Lyman alpha image. So that could really explain why it's easier for the Lyman alpha to escape there. Now, if you look at what happens in the other galaxy in ELAS1, this is the H alpha from PMAS. So we didn't have Muse data for ELAS1 because it's a bit too up north in the sky. So we get a bit less resolution than the Muse, but essentially the star forming sites are coincidence with lower column density H1 regions. And if you look at the Lyman alpha, it's essentially at the same position as the H alpha emission. And in that case, we also see that the Lyman alpha is also on the blue side, although the moment 1 map is a bit more noisy because we have less signal to noise ratio with the last one in the H1. Looking at the 3D picture of it, this is the same as I showed before for last 8. You have the 2 spectra compared. And here what we can see is that there is basically no H1 to the sensitivities we reach with that cube in the aperture. And so that is basically saying that there is lower column density H1 in front of the Lyman alpha emission. And again, you have the channel map that shows really that you don't have much H1 in front of the Lyman alpha there, at least to the detection limit. And so what are the ISM conditions? Okay. So the ISM conditions that seem to enable Lyman alpha escape in last 8 are the redshift of the Lyman emission while the H1 gas is blue shifted. There is also probably some role of the lower dust content that is not destroying the Lyman alpha on the western side of the galaxy. And there could be a link to past interaction and accretion of low metallicity neutral gas that enable that scenario to take place. Now for ELAS1, we seem to have lower column density gas on the line of sight and possibly some redshift of the Lyman alpha emission compared to the gas seen by where the Lyman alpha is located on the moment 1 map of the H1. And so to conclude, this is the first result comparison of Lyman alpha and 21 centimeter H1 emission. We're still analyzing the results, but we have found some points that could possibly explain why Lyman alpha is escaping where it is escaping. And although those galaxies are a bit different from what we see in the high redshift universe, physics is still the same. And so obtaining this type of comparison is a step to determine the intrinsic Lyman alpha spectra from galaxy. And yeah, the next step will be to get more high resolution data, because those two galaxies are quite peculiar and it's only 2 data points. So that would be really interesting to see what happens in the galaxies that are in other places in the parameter space. And we're also going to analyze the low angular resolution data in H1 for the ELAR sample, and to have an idea of how the global H1 properties impact Lyman alpha in all 42 galaxies. And yeah, thank you for your attention and the opportunity.
Better data is always the next step, isn't it? Thanks a lot, Alexandra. You're muted again, and you will need your voice to answer the question that I will now read to you from Casper, asking, from the low redshift Lyman alpha H1 21 centimeter connection, is it possible to predict the H1 content of high redshift galaxies based on Lyman alpha emission, and how it scales and interacts with H1?
Okay, so for the first part of the question, I think we're really not there yet. That is a goal that would be great if we could just look at the Lyman alpha line at high redshift and say, oh, the interstellar medium, in particular the H1 gas, is like that. But it's a very complex picture. And there is, when you look at high redshift, of course, there is the CGM, as Florian showed in her presentation. There is the IGM that start to participate in this as well. So it's really not straightforward to do this. But that would be great. And the second part of the question, I'm not sure I got it.
So predicting how Lyman alpha scales with H1. Would that be possible?
Yeah, so that would be great. So we're going to analyze the global H1 properties such as mass, the global mass, eventually a bit of kinematics as well in the next part of the project. But it's not something that we can do yet.
Okay. If you're so fast at answering questions, you might even be able to answer this one from Ilsang Yun. Why is Lyman alpha so compact compared to the H1? You might think that it was extended because of scattering in the halo.
Yeah, I think that depends on. It's actually quite extended, but I think the H1 is always more extended. And then the thing is that if it's scattered in the halo, it's going to be a bit fainter as well. So you might not see it very well. You might need more sensitive observations to be able to really see a Lyman alpha halo that would be that faint. Yeah,
all right, makes sense. Thanks again, Alexandra. It's a very nice talk. Very nice work, I think. So let's. Okay, I see that Martin Henold has raised his hand. Martin, maybe you didn't miss the introduction, but questions should be asked in the Slack channel because they will stay there. So please ask the question. You can still get the answer from Alexandra. So the next talk is Seichi, who stepped in for Michele, and will tell us about ALMA lensing cluster survey with a multiply imaged, very bright C2 lines from a high redshift galaxy.
Okay, so thank you for the organizer to give this opportunity. So today I will talk about the great outcome from an ALMA large project called the ALMA lensing cluster survey, especially about the first achievement of the spatially resolved ISM studies for typical suballunar galaxy at Epoch of Reionisation. So our paper have been recently accepted for publication, so please also take a look at these papers if you are interested. So during the past decade, ALMA offers a less fine Fred spectroscopic window even at redshift over 6, where the ionized carbon emission is one of the helpful courant lines to understand the ISM property. But as nicely reviewed by Kirsten in this beginning of this session, what we have found is that there is a large diversity in the star formation rate and seed line relation. So some of them are aligned with the local galaxy relation, while others are showing the seed deficit. So there are several possible causes discussed, such as the low metallicity or high ionization parameter, or the lack of photodissociation regions for these seed line deficits. However, given the situation that we generally select the moderate bright target with a spectroscopic redshift, most of the cases relying on the Lima alpha line. So these results might be biased towards very bright object or the Lima alpha emitter population. For instance, the latest deep Muse study suggests that Lima alpha emitter fraction is around 30% at redshift 6. So it would be also required to perform a blind survey to understand the representative picture at the epoch of reionization. So including this context, the ALMA lensing cluster survey called ARCUS have been carrying out a large unbiased survey. So this is one of the ALMA large program to map out 33 massive lensing clusters by setting up 2 frequency tuning, and we maximize the detectability of continuum sources as well as the line emitters. So we achieve a total area of over 100 arc-square-minutes with a moderate data dips, which could be even much reduced thanks to the gravitational lensing effect. So we are carrying out an unbiased wide and deep 1 mm survey with ALMA. So here shows some of the large ALMA surveys so far performed in the area versus data depth plane. So after the lens correction, we obtain the parameter space of ARCUS like this. So ARCUS is indeed exploring the faint regime of the 1 mm survey as well as the survey volume, which provide us with a unique object that couldn't be identified in previous surveys. So for example, about the continuum sources, here summarize ALMA 1 mm map and HST H-band map for some of the lensing clusters. Although we identify some lensing cluster with poor number of detection, we also found some lensing cluster with rich detection at the same time, indicating that we are overcoming the cosmic variance. Even with the robust SN threshold, our number of sources exceed 100, which is one of the largest source detection compared with previous ALMA large surveys. The blind line search analysis have been also done where 60 line candidates are already identified. So careful tests are ongoing, such as spurious source rate estimate, completeness, and counterpart analysis. But before going to the careful tests, we discovered a very reliable bright seed line emitters at redshift 6, which is the main topic of today's talk. So here summarize ALMA spectra and the line intensity in red contour on the HST maps. So in the first step, we detect these 2 bright lines at the same frequency. The optical near-infrared counterparts show a similar SED shape, and the peak of the redshift distribution are in excellent agreement in the case that the line is interpreted as a C2 at redshift 6, shown in this red line. Indeed, this redshift solution is confirmed with the latest GMOS spectroscopy, where we see the continuum break at the expected wavelengths. So, and interestingly, based on this redshift solution, our independent mass model consistently predicts that these 2 line emitters are multiple images, and one of which is crossing the critical line. Moreover, the mass model also predicts 2 additional multiple images in this field. So one of them falls in this ARCUS coverage. So we check the ALMA spectrum for this multiple image as well, and we identify a tentative line detection from it at the same frequency as well. So based on these results, we conclude that these bright lines are the multiple images of a seed line emitter at redshift 6 behind the cluster. After the fitting routine between the image plane and source plane, we find that a subregion of the galaxy is crossing the caustic line, which is stretched out to the elongated shape of that as the arc, while the other multiple images traces the full region of the galaxy in the source plane. So the magnification value is estimated to be around 20 or even around 160 at the arc. Although such high magnification value has a large uncertainty in general, but it is not the case in this system with 2 reasons. First, the configuration of these multiple images works as the strong constraint so that the estimate would not be easily changed. And second, we confirm these interpretation and high magnification values with independent 3-lens models constructed by 3 independent mass modelers. So we think that the high magnification value in this system is really robust. So here summarize the physical property of this system after the lens correction. So 3 times fainter than the characteristic luminosity at this redshift, and both sub-region and 4 region of the galaxy are falling on the main sequence, but star formation versus stellar mass. And based on the 3D modeling result, we also obtain the dynamical mass, and subsequently, we also get the gas mass by subtracting the stellar mass from this dynamical mass. So the gas fraction and the galaxy size also show the average value among the star-forming galaxy at redshift 6. So we conclude that our C2 line emitter is an abundant and representative population of the sub-L star galaxy at redshift 6. Yes. So to see the direct observed picture in the source plane, we also performed the pixel-to-pixel source plane reconstruction. So first, for the one of the multiple image, which traces the 4 region of the galaxy. Since we find several clump features there, those are marked from A to D. So here is the source plane reconstructed map. So this white ellipse corresponds to the source plane HST resolution, showing that we achieve a few hundred parsec scale resolution in the source plane. Okay, next, for the arc, we obtained the reconstruct map presented in this inset panel, where the lens corrected luminosity reaches down about 1% of brightest peak in the 4 region. Interestingly, we find that this luminosity distribution from the arc perfectly matches with the position of the faint clump seen here, dubbed E, which is away from the UV brightest peak by 1 to 2 kiloparsec in the reconstructed map from the another multiple. So then this nicely illustrates the power of lensing, making the faintest outskirt emission from the galaxy highly visible, which is almost invisible in the other multiple images, even with the magnification factor around 20. So the C2 line distribution are also reconstructed and find that its effective radius is around 2 to 3 times more larger than the rest frame UV one, while the C2 peak position are consistent within the errors from the rest frame UV peaks, both in the sub-region and 4 region of the galaxy. So based on the current data depth and resolution, we interpreted that a majority of C2 line is arising from the rest frame UV emitting regions. And thanks to this unique system, we now address the C2 luminosity and star formation relation from the spatially resolved ISM to the 4 galaxy scales for a typical sub-L star galaxy at the epoch of reionization for the first time. So after the lens correction, we find that both sub and 4 regions of the galaxy show the relation consistent with the local galaxy relation within the dispersion. While we see that the sub-region of the galaxy show a bit higher ratio, so the C2 over star formation ratio, a bit higher. So to address this slight difference, we also measure the rest frame UV size and plot C2 over SFR ratio as a function of star formation surface density, which is known to have an anti-correlation that is explained like the high ionization state at the high star formation rate density regime causes the C2 deficit. We find that slightly higher value in the subregion is consistent with this known trend here. So this slight higher ratio in the subregion would be caused by the sufficient offset from the UV brightest center, and thanks to it, the ionization state being kept moderate and having a higher C2 emissivity. So given the unbiased aspect of the ARC survey, our successful at least one C2 line detection allows us to place the lower limit of this in the C2 luminosity function based on the entire survey volume of our ARC.
It's 2 minutes left, Seiji.
Okay, thank you. So we find that lower limit is consistent with the current semi-analytical models, but we caution that we didn't apply any correction for our estimate, like the completeness correction. So since our sources are spatially resolved and extended morphology, the completeness could be low, and this limit could be pushed up a bit higher. So we thus also derive another prediction by combining the star formation rate function at redshift 6 and the local C2 and the star formation relation, which is shown in this blue line. We find that our and previous constraints are all consistent with this another prediction, which might suggest that the local C2 and the star formation relation is widely valid. So in this last slide, I'd like to give a kind of brief summary and brief discussion. So in this talk, we overview the result in several different scales. So we find that co-spatial distribution between C2 and rest frame UV from the ISM to the 4 galaxy scales, where the C2 and star formation relation are consistent with the local galaxy relation. We also address the statistical results in the C2 luminosity function, which is more or less corresponding to the cosmic scale of the universe, where the prediction based on the local C2 and star formation relation is consistent with all of our and previous constraints so far obtained. So although our result relies on one galaxy, given the unbiased aspect of the ARC survey and the representative sub-L star galaxy property of our C2 line emitter, our result might indicate that the C2 and star formation relation estimated in the local galaxies might be universal for a wide range of scales, including the spatially resolved ISM, the 4 galaxy, and cosmic scales. Okay, so here is a summary. So the ARCUS is uniquely exploring the unique 1 millimeter faint regime. And so we now discover very interesting objects that have been not discovered in previous survey. So yeah, thank you.
Thanks a lot, Seiji. I have a question. So maybe because I don't know about lensing models, so you actually see quite a nice detail in for such a high redshift galaxy. But how much does the actual structure of the ISM depend on the lens model? I mean, how certain can you be that it's like this?
Okay, so can you see my slide?
Yes.
Okay, nice. So so in our team, we construct 3 independent models, and this time, yes. So these 3 models are constructed by independent modelers, and we obtain the consistent interpretation and the consistent magnification values. This is thanks to the strong constraint obtained from this multiple image configuration. So in this case, we think that interpretation and the magnification value will be very solid.
Okay.
So yeah, these
cool.
3 models. Yeah.
All right. Thanks a lot. Any further questions can be written in the Slack channel. I see that there's suddenly coming more questions, but you can answer these questions in the channel, and the rest of us will move on to the final talk. Thanks a lot, Seiji. It was great. The final talk, before we take a short break, by Justin Spilker from Texas, who will tell us about molecular outflows. So Justin, please share your screen. You already shared it. Thank you.
Okay. Does that show up okay?
Yep.
Okay, great. Yes, my name is Justin Spilker. I'm a Hubble Fellow here at the University of Texas. I'm very glad to have the electricity to be able to bring this talk to you today. I'm glad this workshop is this week and not last week, for sure. So I want to talk today about the first sample that we've built up over the past few years of molecular outflows in the very distant universe. These results are based on a couple of papers that you can see referenced there at the bottom, and all the data and tables and everything from the papers are available on our collaboration website. And so this was a project that was really kind of inspired by the realization over the past 10 to 15 years that things like feedback and outflows are really essential for the way that galaxies form and evolve. So I don't have a lot of time to go into all the ways that feedback and outflows influence galaxies, but it ends up being this really sort of tentacle scenario where the feedback influences a huge range of observables, a huge range of properties of galaxies, all the way from the way that they inhabit dark matter halos to the way that their metal contents evolve with time. Feedback connects black holes to the galaxies that they live in and sets the overall efficiency of star formation. And so it ends up being really critical to sort of understand how this feedback impacts the galaxies that we observe across the universe. And in particular, since stars form out of molecular gas, the impacts that feedback has on the molecular gas ends up being quite important for the way that they evolve over the long term. So for example, if you want to make a quiescent galaxy, you probably need to be able to keep that galaxy from having molecular gas that it would otherwise turn into stars. And even way early into the history of the universe, we know that that feedback must have been operating. This is just one example of a very massive galaxy that we know existed at as early as Redshift 4. The stellar mass is about 10 to the 11 solar masses. And if you don't speak optical spectroscopy like myself, you can tell that this galaxy is quiescent because of the label here on this upper image that tells you that it's quiescent. And if you basically just do some quick math, divide the mass by a star formation rate in order to form this amount of mass by Redshift 4, you find that the star formation rate that you would need to form a galaxy like this is much, much higher than the typical sort of star formation rates that you get from UV bright galaxies in things like the HST deep fields. And so what that basically tells us is that the sort of typical galaxies that you might see in an HST image are not the ones that are forming these really massive early quiescent galaxies. And instead, it's probably coming from galaxies that are much more dust obscured. And so they don't tend to show up in the small area surveys from things like Hubble. And this has been sort of speculated about for a long time now, actually. For a lot of reasons, we think that dusty galaxies are probably the progenitors of these earliest quiescent galaxies. Just in terms of their star formation rates, their masses, the dark matter halos that they live in. All of these sorts of circumstantial lines of evidence point towards the fact that these galaxies, these really dusty galaxies, are probably going to become the first generation of quiescent objects. And so I'm just going to sort of assert that if that's true, we can use these very distant dusty galaxies as, I guess you would call them, laboratories for the way that feedback operates in the early universe. And the basic reason for that is just because if these galaxies are going to form stars very quickly and then stop all the way by Redshift 4, some physical process or processes have to be in effect to basically prevent that star formation from resuming, at least in the short term. And so the sample that I'm going to use for this, just to cut 5 years of work down to one slide, is coming from the South Pole Telescope survey, which surveyed a huge area of the southern sky. And from that, we have assembled a sample of about 100 galaxies that all have spectroscopic redshifts. And by virtue of being bright, they all basically all happen to also be gravitationally lensed. And so this is great because now with all of these redshifts, we can go and basically pick any spectral line that we want in order to study this sample in whatever way you might desire. And the lensing also ends up benefiting us because it means that we can get higher spatial resolution than you would otherwise be able to get, similar to Seju's talk that he just gave 15 minutes ago. And so to study the properties of feedback here, the observational tracer that I want to use is going to be this molecule called OH, hydroxyl. There are a lot of reasons that this is a really great tracer of molecular outflows in particular. It's a really simple molecule. It's easy to form. The abundance is high. The transitions are really strong. And we have a long history of observations of these lines of OH with Herschel in the local universe. So it's just a really nice, easy built-in comparison sample. And so the signature that we're looking for here is this blue shifted line wing. So this is basically the fact that you're seeing this line in absorption tells you that the gas is in front of the galaxy. The fact that it's blue shifted tells you that it's moving towards you. And so the fact that you can combine those two little pieces of information tells you that these must be outflowing, this must be outflowing gas. And so I'm targeting a sample of about 11 galaxies from this SPT survey from Redshift 4 to 11. It still ends up being fairly high frequency observations. So it took ALMA a little while to build up a nice size sample. This ended up being several years of observations in order to line up the good weather season with the right array configurations for ALMA. But now that it's done, we have a nice sample of about a dozen galaxies with these observations of OH. And so just to sort of cut to the quick, here are all the OH spectra from the entire sample. OH happens to be a doublet, so every time you see one absorption line, you actually see two, which is why most of these absorption lines are double peaked, or double troughed rather. And what you see is that in many of these cases, we actually see these really strong blue shifted line wings. For example, this one down here in the lower center, we don't even get all the way back up to the continuum level after 1,000 kilometers per second of bandwidth. And so if I go through and carefully sort of classify which ones of these have outflows and which ones don't, we wind up finding that a huge fraction of them have outflows. There's something like 3/4 of the sample. And so since we're seeing this in absorption, what this tells you is that A, the outflow rate, just in terms of the occurrence rate, has to be very high. And B, the covering fraction or opening angle has to be very high as well, because otherwise you wouldn't be able to detect an outflow in absorption towards such a high fraction of the sample. So people always ask me about the outflow rates. And so here I've just sort of assembled the biggest sample that I could find of outflow rates in the low redshift universe. These circles are all objects that were also observed in OH, and the squares are objects that were observed in CO. And so if I throw our redshift 4 sample on here, we found that basically they have very high outflow rates. This probably isn't all that surprising because these are among the most highly star-forming galaxies in the entire universe. And so you would probably expect that they should have high outflow rates. What might be a little unexpected is that the loading factors, in other words, the outflow rate divided by the star formation rate, are a little less than 1. So basically these galaxies are growing faster than they're able to expel the gas. And this is maybe a little bit surprising compared to similarly highly star-forming galaxies in the local universe. But one issue, I think, is that these outflow rates and the energetics of these outflows are really highly uncertain. I'm giving you these outflow rates, but there's a lot of assumptions that go into this as far as the geometry is concerned, as far as the abundance of molecules is concerned, and so on. And there's not really a whole lot of ways to get around this, to be honest. At least for the next several decades, we're going to need some sort of new facility that will give us a better chance to constrain these outflow rates. So even in a case where I've observed the outflows directly, I'm not even trying to infer what the outflow rates might have been based on other indirect tracers like mass or metallicity or any of these sorts of things. I'm still not super confident that we're getting these outflow rates correct to within a factor of 2 to 5 at best. And so I'm actually going to argue that one better way to constrain outflows and feedback in simulations is actually going to come from the structure of outflows themselves. And so I'm just showing here 2 different simulations of outflows. On the left, the molecular gas in outflows winds up only surviving in these really small chunks. So basically anywhere where the yellow gas here on the left has survived into the outflow, the molecular gas, it winds up being in these sort of 100-ish parsec sized clumps, but there aren't very many of those clumps. On the other hand, on the right, the molecular gas sort of reforms out of the hotter material as the outflow sort of expands. And in that case, we basically will have no hope ever of resolving the structures in these outflows because they wind up on scales of about 10 parsecs. And that's just not really feasible to resolve with any realistic facility in the near future, or even the distant future for that matter. And so the point is that the details of how feedback is implemented in these simulations lead to really large differences in the structure of the outflows. And because we have a lens sample, this is something that we can actually constrain. So after a lot of math and work, we can reconstruct the intrinsic structure of what these outflows look like. And so here's just one example of a galaxy at redshift 5.3. The continuum emission from the dust is pretty smooth. We don't really see any signs of structure there on scales of a few hundred parsecs.
2 minutes left.
Yep, thanks. But what's cool is that on the left here, the outflow absorption, this is separating out only the emission or only the absorption that is definitely in the outflow, shows this kind of clumpy structure where we see a few different clumps separated by a few hundred parsecs. And that's actually ubiquitous amongst the sample. So here's just the gallery of all of the targets where we detected outflows. And you can see that these clumpy structures are really common, actually. And so I can tell you that it looks like we are not in sort of a spherical cow kind of scenario where these outflows are just sort of propagating, sort of uniformly in a spherical fashion, it looks like it's a really highly clumped structure. And so I can tell you that these outflows look like they're clumpy, but the resolution of the data that we have now doesn't actually let me constrain the size of the clumps themselves. So in other words, I can tell you that there are multiple clumps, but I can't tell you how big those clumps are. But to sort of boil down an argument that took a few pages of the paper, from optical depth arguments, I can sort of predict that in order to resolve the clumps directly, we're going to need to reach resolutions of about 50 to 100 parsecs. And that might sound crazy, given the typical size scale of galaxies in the distant universe, but this is actually achievable in the distant universe with lensing. This is only about 2 to 3 times higher spatial resolution than the data that we already have. And so it's actually possible, I think, to get down to these really, really fine spatial scales in the very early universe to figure out the structure of outflows. And I think it's going to be a really powerful tool. So just to summarize, this is the first sample of molecular outflows in the very early universe. We found outflows in a huge fraction of the sample, which is good. So if you are out there in the audience sitting on samples of galaxies that seem like this might be viable, it doesn't take a very large number of galaxies to probably convince yourself that just by luck you'll have at least a few outflows. They look clumpy on scales of a few hundred parsecs, but I can't actually tell you what the size of the clumps are at this point. And I think the sort of interesting idea is that it might be more useful to constrain simulations with the structure of outflows than the actual outflow rates or energetics themselves. So I'll stop there. Thanks.
Yeah, thanks a lot, Justin. And nice allusion to Seiji's talk about how to achieve the high resolution. So there's time for a question. I'll skip my own and go to Ilseng. You already had one. I go to Chen Tao maybe, who asks, in one of the spectral plots, the OH absorption seems to have a redshifted component. Is that an inflow?
Yeah, so you're right. So Chen Tao's right. If in theory, in principle, you can also use this line to trace inflows. In that case, you'd be looking for redshifted absorption instead of blue shifted. I'm not convinced that any of these actually show inflow. We didn't set up the observations, right? ALMA has a limited bandwidth, so I'm showing you basically the entire velocity coverage that we have. So I didn't set up the observations to have a really good coverage of the redshifted side of the line profiles. A few of them, for example, this one up here in the top row, looks like the OH is peaking towards the redshifted side. But I think the key issue with the interpretation of this actually comes from having knowledge of what the C+ line is doing. So in this case, you actually see that the C+ is double peaked. And so probably this galaxy is just a merger. And so this is kind of the dirty laundry bit of interpreting absorption lines in the high redshift universe, is that the galaxies themselves are pretty complicated in terms of their kinematics. And so when I classify things as outflows, I'm only picking them as outflows if they're more blue shifted than any of the emission that I can see. And so in this case, for example, even though this line profile is slightly redshifted, that could mean that it's outflowing from one component of a merger. It could be inflowing towards the other component, or it could just be systemic absorption coming from the interaction region. So for example, if you look at the antennae galaxies in the nearby universe, most of the emission, most of the action is coming from the area where those galaxies are crashing into each other. And so I'm not claiming any inflow here, although in principle, yes, it is possible that you could use this line to do that. I think you would just want to pick a sample of galaxies that's less complicated in terms of what their kinematics look like.
Okay, interesting. Cool, thanks a lot. So there are several more questions in the thread that you can answer while we take a short break of 4 minutes. It's going to be. Thanks a lot to Justin and to Seiji and to Alexandra and to Florian. We'll meet in 4 minutes for the next session.
Can you hear me? I am Maria.
Yes, we can.
Okay. Yes, I see that our first speaker for the next section is Miroslava, but I don't see her in the participant list. I think that we need to start the second session. I don't know if Miroslava is ready for the talk. Because if not, we should move to the second talk by Denis Burgarella.
I'm here if you need.
So perhaps we can start with Denis, and then if Miroslava connect later, we follow with her talk. So we can start with the talk by Denis.
Okay, so
are you ready?
Yeah, you see my screen?
Yes, perfect. But not as a presentation. Now, yes. Thank you.
Okay, you have one slide only. Okay.
So our next speaker is Denis Burgarella from Laboratoire d'Astrophysique de Marseille, who will talk about the dust cycle in galaxies at redshift between 5 and 10. So please go ahead.
Thank you very much. Thank you for inviting me. So you have here the list of my collaborators in Europe, in Asia. And so there are three major problems at the origin of this work. The first one is how can we explain the large amount of dust that we see in the early universe? And all these points are studied in the paper listed at the end. So we'll see now about the first one. So just to summarize, when we have stars formation and stellar evolution, we know that supernovae and AGB star can produce dust. These dust go into the ISM that can be destroyed by supernovae as well. But also you can have dust coagulation accretion in the interstellar medium, which will later go into the new star formation. So this happens in galaxies. But you have also outflows, and we know that at high redshift, outflows are very strong and ubiquitous in high redshift galaxies. So this is also very important, and we need to take this into account. This is a diagram that I borrowed from Lezhnevskaya and Michalowski, and you have the redshift at the bottom and the dust yield per star on the y-axis. You have two main physical processes that could produce dust grains. AGB at the bottom in blue and supernovae at the top. as you can see, immediately it's very difficult to form enough dust to have to reach what we have at high redshift, whatever the redshift between 8 and something like 9, and whatever the initial mass function. So that's because of 2 points. First, not enough dust production, but also it's very early in the universe at this type of redshift. On the other hand, at the top, it seems that the yellow, which represent dust produced by supernovae, it's possible to reach these galaxies. But it depends on the assumptions on the dust destruction. If you assume 90% destruction, you see that it's not very likely that this galaxy can be reached. But we know that there is a lot of debate about this dust destruction by supernovae. The level of destruction can be different. Also, you can rebuild dust after the destruction. So that's something that we that can be studied further. Sorry, here's a way. The next point is how can we, as was mentioned by Kirsten at the beginning. So this is quite important. And you see here in this diagram where you have the Rx, infrared to UV luminosity ratio as a function of the slope, that in the redshift range 5 to 6, Face et al., Kappa et al., you have a few detections, but you have a lot more undetections. And this is a problem because, well, we have some detections, but the objects that are not detected here have at the same time a very low dust attenuation, but also they are quite red. And of course, we want to understand why. And that's what we did here. So we built a sample of 18 Lambda galaxy in the range 5 to 10 approximately. All of them have spectroscopic redshift. They have been observed in subnanometer with ALMA. When you fit them, you find that they are low stellar mass and probably low metallicity objects, which is consistent with redshift. So we assume simple star formation history because they are simple galaxies. Sometimes we have C2 detections that we use to further constrain the star formation rate. And finally, we fitted these objects with the code CIDER. So as you can see here, we have a few objects from the previous list. And of course, it's immediately obvious that we don't have a lot of data. In most objects, these one are upper limits. Sometimes we have a few points, but it's very difficult. And we cannot constrain the dust characteristics and the dust emission in the rest frame far infrared subnanometer. So we can wonder how we can densify this information and obtain a more regular sampling here. Of course, one way would be to observe more and deeper, but we know that it's not very easy and even difficult or impossible for some objects. So what we try to do is to select the sample which is detected with ALMA. So we have our objects, and then we use the redshift as a spectrograph, because when you assume the given band with ALMA or NOEMA or whatever you get, because the redshift changes, you sample the infrared acidity. And this is very powerful because it allows you to get some information. Of course, that means also that you assume that these objects have the same properties, that they are all selected in the same way, and the acidity is consistent as well. Also, we normalized all these acidities, the observed one, at 200 microns, because first we assume that the dust is transparent at 200 microns, and also because, as you can see, we don't have any point at larger wavelengths, so it's not meaningful. And because of the redshift range, as you can see here, we can cover quite a good range of wavelengths. And this is the dust temperature, assuming a modified blackbody from 30 to 85 K. And if you do the acidity fitting here, you get something where the dust temperature is around 50 something Kelvin. But what we wanted to do first is to have one template which is valid for these high redshift metal poor LBGs, and to use this template to fit it with CIDER, estimate the parameters, and then apply it to the far infrared undetected LBGs. That allows to get free from the parameters. You assume only one single thing, and you can focus on the other properties. And well, it seems to work quite well. This is using Drain-Henley models, and so you see that we follow quite well one of the law. no, sorry, this was a modified blackbody, and this is randomly models, and we use both, and it was quite well, as I told you. And we estimated the main parameters. Mainly, we use a specific star formation rate, the specific dust mass divided by m star, and we also use a parameter which is h divided by tau, assuming the delayed star formation history. In other words, this is the percentage of the burst in the star formation event. And so we get something which is quite young, as you see. In this diagram, which is one of the output, you have the specific dust mass here versus the specific star formation rate, color-coded as a function of h divided by tau main. Well, you can assume tau main 100, so that tells you that here you have 800 million years, and well, here 100. And what you get here is this type of diagram for high redshift LBGs. The first thing that you see that it's less dense here, which probably means that the evolution is fast. Then you have upper limits on the right and on the left. But as you can see from the color, they are different. These one are for young objects, this one for old objects. So that means something. And what you assume here is that there is an evolution. So here the galaxies are moving up, then they are detected. So here they don't have a lot of dust, as you can see from this. This means that they are not detected with ALMA. They are detected here, and after that, the dust is removed or destroyed. And we can confirm this by color coding by the IRX, so the dust attenuation, basically. The one here are less dusty than the one in the middle. So that's an information. To compare with, we use a sample of low metallicity, low redshift galaxy, a dwarf galaxy sample. That's here. And as you can see, if I move from the previous slide, I cannot. So this is the trend for the high redshift galaxies. So you see that it extends to lower specific star formation rates. And if we want to explain why, well, we need to use the metallicity. That's the main parameter. And you see that to populate this area, I remind you that the LBGs are down at this arrow. To populate this area, we need larger metallicity objects, maybe SMG at high redshift. That's something we need to check. We didn't right now. So we model this, and we use a lot of models, as you can see here. We fitted the models, and the summary of this is that you have the specific star formation rate on the left and the age on the right. And the summary is that you build dust quite fast here on this part at low age or high SSFR. Then the dust is destroyed by supernovae, about 20%, but mainly removed in the intergalactic medium. And if you assume the growth in ISM or aspiration, it would go this way. So this is for another type of objects, not for these high redshift LBGs. And this is very consistent. You notice that you have two main groups of curves. This one, the top one, is for a top heavy IMF, and it seems to work better for our objects. So if we come back to this diagram, assume a formation here, we form dust, and the dust is destroyed. So of course, some objects are picked when they are at the top, and other when they are in the phase. So now we look at the IRX beta diagram, and you get the same thing. Young and blue objects, thank you. And then time and old and red. So these objects are old and red because, well, that's the evolution. Very fast, so I now added the alpine sample. So that's a similar sample, but at lower redshift. I did the same job, normalization here. And with 500 realization on 0, you see that we have an even better SED with, well, different realization. And the dust temperature for several realizations, the beta emissivity, seems to indicate something in the range 40 to 60 K. I'm still working on that. The last point is the dust attenuation versus stellar mass versus redshift tension. We know that some people are thinking about having a linear relation for the IRX stellar mass. But if you integrate this for the galaxy, assuming the stellar mass function, you are well below. You cannot explain the evolution of the dust attenuation with redshift. To explain this, you need first to have an evolution of this law with redshift. And also, you need to have something which is flat here, meaning that you have a non-zero apparent dust attenuation at low stellar mass. And this is assumed by some models. If you do this, you are back to what is observed. So this is very important for modeling these galaxies. If you don't do that, you will have problems with the low stellar mass galaxies. Okay, so I just give you my results because I see I'm late. Thank you.
Well, thanks, Dennis, for such a nice talk. We have time for a few questions. I am here looking in Slack. Well, Andreani say the error bars on the dust mass are very small, while we know that it is not an easy parameter to estimate. Why that?
On the stellar mass, only you can see this in the table, because here that's not zero on the stellar mass, that's on the specific, on the dust or on the stellar mass, sorry, can you repeat?
Yes, the error bars on the dust mass are very small.
Oh, yeah, on the dust mass. Okay, so that's something that you have here. Well, the point is that because I have my modeling and the point here are estimated from the acid fitting, that's the uncertainties I get on the dust mass. Of course, that's model dependent, and these uncertainties can be larger if you assume something different. But the set fitting provides me with assumptions I had. Well, I don't have time, you can look at the paper, and it's quite consistent with what we have in this type of diagram. If you assume something larger, the main information here is this. You have upper limits on the edges and detection at the center. This is the most important information.
Okay, thank you. There are many more talks. The second one is by Il-San Yoon. How do you break the degeneracy between the dust temperature and redshift in the CIDER fitting? Do you have a spectroscopic redshift?
Yeah, well, that's a very good question. Actually, as you can see here, we have quite a large range of emissivity. First, we have spectroscopic redshift, so it's okay. But yes, we have something which is quite large on the emissivity and more picky on the dust temperature. So that means that we have some uncertainties, but this is consistently taken in the acid fitting. And when we assume, or maybe you can see here on the alpine sample. Let me go fast. Yeah, here. You see that the dust, this is 3 out of the 5 regularization. You see that the peak is quite narrow for the dust, but you move from 1.5 here to more than 3 here for the emissivity. So that means that we don't constrain this emissivity. And what we try to do usually is to, well, I didn't do it right now, is to fix, do the acid fitting with 1 emissivity and check what we get on the dust temperature. And if the dust temperature remains, well, within the uncertainties that we have here, that's okay. If not, that means that we cannot estimate. In this case, it seems that even though we have some large uncertainty and beta, the dust temperature is taken by this trend that we see on the left.
Well, thank you very much. There are many more questions, but you can continue the discussion in the Slack channel. Thanks again, very interesting work.
Thank you.
I don't know if Miroslava is here.
Yes, I'm here.
Okay, sorry.
Yeah, I'm really sorry for the delay. I had a problem, so sorry for that.
No problem. Well, so are you ready for your talk?
Yes, I can share my screen.
Okay, well, our next speaker is Miroslava Desauches-Sabatsky from Geneva Observatory, who will talk about assessing the molecular gas content of galaxies toward the cosmic reionization epoch. Please go ahead.
Thank you. So can you hear me? Can you see my slides?
Perfect, yes.
Okay. So thank you for the organizer to give me the opportunity to present here my work on how to assess the molecular gas content of galaxies toward the cosmic reionization epoch. And I would like to begin by motivating why assessing the molecular gas content of galaxies is essential. So the understanding of galaxy evolution relies on two fundamental pillars. The first one, now known since decades, tells us that high redshift galaxies had high star formation rates, as corroborated by the measured rapid increase of the commuting star formation rate density, which reached a peak at redshift of 2 and had been gradually declining since. The second fundamental pillar is that high redshift galaxies seems to be characterized by large molecular gas contents. And indeed, thanks to the ALMA deep field surveys, there is now a growing observational evidence that the co-moving molecular gas mass density follows a similar evolution to the star formation rate density across cosmic time. Although very large uncertainties are still present at redshift larger than 2.5, where the molecular gas mass density evolution still needs to be ascertained. So this co-evolution of the molecular gas density and star formation rate density is expected since the cold molecular gas is the fuel of star formation. It is, however, still unclear how the galaxies assembled, how first they acquired this large reservoir of gas, and what did induce these high star formation rates. So two main scenarios have been suggested for that. The first one is a high merger rate at high redshift, which could drive quiescent galaxies into bursts of star formation. And the second is a high cold gas accretion rate from the cosmic web that could lead to higher gas densities and star formation rates. So strong support toward the cold gas accretion flows comes really from the existence of the star forming main sequence, which you know that 90% of galaxies contributing to the star formation rate density reside on this main sequence, which relates stellar mass and star formation rate. And the normalization increase with redshift result in the rise of the specific star formation rate with redshift. What is very important is the tightness of this main sequence with a dispersion of 0.3 dex only, which indicates that the star formation at high redshift is not driven by merger-induced starburst, but rather by a continuous mass-dependent supply of fresh gas from the cosmic map that sustains this quiescent star formation for several giga-years. And indeed, with Andreas Feist, we have recently found that the main sequence seems to be already in place at redshift of about 6, which means 1 giga-years after the big one, as shown with the alpine samples of 118 galaxies at redshift between 4.5 and 6, selected for the ALMA large program to investigate C2 at early times. So this implies that similar star formation processes had to really regulate galaxies over giga-years to keep them on this main sequence. So based on this second and third item, the main sequence is often interpreted in the terms of this gas-regulated model in which main sequence galaxies really lie in a quasi-steady state equilibrium, whereby star formation is regulated by the available gas reservoir, whose content is replenished through pristine gas accretion inflows and eventually diminished by the amount of material ejected by the galaxies in the intergalactic medium through outflows. So is this the correct picture? To answer to this question, really molecular gas measurements are needed. So while H2 is the most abundant molecule in the universe, it is nevertheless difficult to detect in cold media because it features no emission line with excitation temperature below 100 Kelvin. Thus, free interact cold H2 gas tracers are commonly used to estimate the H2 content of distant galaxies. First, the CO rotational transitions, then the dust mass inferred from the feet of the thermal far infrared dust SED, and finally the cold dust continuum emission measured in the Rayleigh-Jeans tail regime of the far infrared SED. The free H2 tracers have their caveats and their weaknesses. So the NOEMA and ALMA interferometers largely contributed to assemble the molecular gas mass census from redshift 0 to redshift 4 to 6. However, this molecular gas census is really biased toward massive and luminous galaxies and against galaxies at redshift larger than 4. And this is because of the surface brightness dimming, which goes as 1 plus z to the power 4, and also because of the lower metallicities that are expected for high redshift galaxies, making CO dark and thus rare. And this is in fact shown in this bottom left figure, where I precisely show the stellar mass distribution of galaxies with molecular gas mass measurements inferred at redshift between 1.6, and they have all a median stellar mass larger than 10 to the 11 solar masses. And in summary, there are very few molecular gas measurements for main sequence galaxies at redshift larger than 4.5. So to remedy to these biases against molecular gas measurements at very high redshift in main sequence galaxies with typical stellar masses, we have obtained the first molecular gas measurements in 44 main sequence galaxies from the alpine sample at redshift between 4.5 and 6, with a median stellar mass of 9.8 using order H2 tracer, which are first the fine structure C2 line and the dynamical masses inferred for resolved alpine galaxies. So just a parenthesis on the C2 emission. So C2 emission is very complex because different ISM phases like ionized, neutral, and molecular are contributing to it. And therefore, C2 may arise from PDR regions produced by UV radiation from massive stars, hitting the outer layers of molecular clouds, and therefore C2 luminosity has been extensively studied as a star formation rate tracer. But also, the C2 emission may arise from the CO photodissociation into C and C+ in the cold neutral medium of molecular clouds, and therefore it was suggested to examine C2 luminosity as a molecular gas tracer. And to validate the C2 luminosity as a robust molecular gas tracer for alpine galaxies at redshift between 4.5 and 6, we compare in the left panel the molecular gas masses derived from the C2 luminosity using the Zanella and Toll 2018 relation with the molecular gas masses obtained from the dynamical masses for the spatially resolved alpine galaxies. And in the right panel, we compare for the alpine galaxies detected in the far infrared dust continuum emission, the molecular gas masses derived also from the C2 luminosity, but this time with the molecular gas masses estimated from the 850 micron dust continuum extrapolated from the 158 micron emission. And we find that we have a good agreement between this molecular gas mass estimate with different tracer for the alpine sample. So trusting C2 luminosity as a molecular gas tracer, here is what we find. So this figure shows my compilation from the literature of measurements of molecular gas fraction derived from CO detected main sequence galaxies in 5 redshift bins, together with the molecular gas fraction obtained for the C2 detected alpine galaxies shown in red. So what we observe is that the molecular gas fraction steeply rises with redshifts to flatten off above redshift 3.5 and reaches a mean value of 63% at redshift between 4.5 and 6. So this shows that really there are high gas fraction which testify of large gas reservoirs that were present in galaxies at redshift of 6 to fuel really the rapid increase of the star formation rate and the stellar mass during the early evolutionary phase. So the molecular gas fraction, interestingly, perfectly matches the specific star formation rate evolution up to redshift of 6, as shown in this figure. And indeed, the new specific star formation rate data point shown here by the orange stars provided by the alpine galaxy samples support also a specific star formation rate flattening toward high redshift. And this link between the gas fraction and specific star formation rate evolutions result from the interplay between the cosmic inflow and gas consumption rates modulo outflows as expected in the framework of gas-regulated model. So what we...
2 minutes left.
Yes, what are these gas consumption depletion timescales? So in this figure, I show again my compilation of CO-detected main sequence galaxies together with the alpine galaxies shown in red, and we observe really a shallow gas consumption timescale toward high redshift, with only a factor of 2 to 3 shorter values at redshift between 4.5 to 6 than present-day galaxies. So this gas long consumption timescale suggests that the star formation is inefficient in main sequence and that galaxies must be continuously supplied in gas to enable them to sustain high star formation rate for several gigayears. And as a consequence, the large molecular gas content does appear as the main driver of the specific star formation rate increase with redshift. So what we also observed is there is a big scatter that we can observe at all redshift, both for the molecular gas fraction and gas consumption timescale. And this results from a multifunctional dependence on various physical parameters, such as the galaxy offset from the main sequence, the star formation rate, and stellar mass, but also with different galaxy evolution for different galaxy population. This is precisely what I would like to explore here. So what we have done is for the first time to look for the gas mass evolution of specific galaxy population selected with the multi-abundance matching, which links as a function of redshift the growth of dark matter halos as derived from numerical simulation with the growth of stellar mass constraint from observation. And what we find is that the alpine galaxies appear as the progenitors of Milky Way-like galaxies at redshift 0 in dark matter halos of 10 to the 13, stellar mass, and of more massive galaxies in 10 to the 14 solar mass halos at redshift 0. And what we find is that they show very different galaxy evolution. So the Milky Way-like progenitors show a monotonic decrease of the gas fraction with cosmic time, reflecting kind of a closed box evolution, while the more massive progenitors shows a constant molecular gas fraction from redshift 6 to at most redshift of 2 and a very steep decrease below redshift of 3. So this flat gas fraction evolution at high redshift for the more massive progenitors may be attributed to 3 effects. First, a possibly very efficient star formation during the early evolutionary phases of these massive progenitors, such as that the infalling gas is rapidly converted into stars. And second, if the outflow is present, they may blow part of the infalling gas and quench the star formation. And as shown in the right inset, we have shown with Michele Ginolfi and Seiichi Fujimoto that there is evidence of star formation-driven outflows which are yielding the extended C2 halos that are detected for the more massive and star-forming alpine galaxies. And finally, we can also suggest by simulation that for very massive dark matter halos, the gas supply start to switch off and prevent star formation. And this is due to the fact that as larger halos grows, it reaches a threshold for the virial shock heating. And as a consequence, the infalling gas shock heat ups and reaches the virial temperature. And for our data, this suggests that this may be happening really at redshift of 5 in 10 to the 11.5 halos, and this indirectly implies that these massive galaxies must be mature by redshift of 6 and probably quench earlier than lower mass galaxies. And thus I'm running out of time, so I leave you here with my main conclusion. So thank you.
Well, thank you very much, Miroslava, for such an interesting talk. And we have time for a very short question. We have a question by Ilsan Yun. How significant the cosmic variance is in the molecular gas fraction measurement from different surveys across this wide range of redshift?
That's a good question. It's true that that is something not really which is checked, but it's true that this compilation of different molecular gas measurements come from different surveys. So there is not really probably a bias with cosmic variance, but it's true that it has not been specifically studied to see whether there could be some inducing biases in this gas fraction evolution due to that.
Well, thank you very much. You can continue the discussion in the Slack chat. Thank you again, Miroslava. And well, we now move to the last talk by Ryan Sander. So our last speaker is Ryan Sander from the University of California, and we'll talk about understanding the ISM metallicities and nebular emission lines at redshift greater than 6 using ALMA and JWST synergy. Please, you can start.
All right, thank you. Hi, everyone. Happy to be talking to you today, and thank you for the Sazerac SIP organizers for inviting me. I found Steve Wilkins' cheeky comment about choosing the title to exclude the H2 astronomers a bit ironic, because myself, an H2 astronomer, has managed to infiltrate the workshop with an abstract about H2 physics, but with very important connections to the cold ISM and our interpretation of it. So I hope that you'll see those connections today. So I'm going to be talking today about galaxy metallicities, and in particular how we're going to measure those in the epoch of reionization. And I'd just like to convince you very briefly by way of motivation that metallicity is a very fundamental property that's important for many science cases about the ISM, many of them very important to reionization and also very important to the cold ISM. And so here's a non-exhaustive list of some of these cases. And we've heard in many of the talks already the mention of how metallicity is very tightly connected to many of these science cases we've been discussing. We can measure things like the mass metallicity relation to get constraints on gas flows and baryon cycling in galaxies. Metals are, of course, related to the integral of the star formation history of galaxies. And so in particular, in the very early universe, finding galaxies with moderately high metallicities places very tight constraints on the star formation histories and also when the first stars formed in these galaxies. We see in the local universe that ionization conditions and metallicity are very tightly correlated. Things like the ionization parameter shown in the top panel here anti-correlate with metallicity. And understanding the ionization conditions is important for understanding questions like the O3 to C2 ratio that we already heard about today. And also understanding the properties of massive stars and the ionizing photon production in massive stars that powers nebular line production. Chemical abundance patterns, such as the carbon or nitrogen to oxygen ratios, depend on metallicity, as we see in lower redshift samples. And of course, understanding the carbon abundance is very important to interpreting C2 observations that we've seen, also observations of rest UV lines like carbon-3 from very high redshift sources. Of course, dust is very closely related to metals, as we heard in Dennis's excellent talk. And metallicity is essentially a key link between dust, gas, and metals. You know, we talk about the dust to gas ratio and the dust to metals ratio, but metallicity is just the metallicity to gas ratio, so tightly related. And then, of course, the CO to H2 conversion factor also depends on metallicity. And so the question I'd like to answer in this talk is basically, how are we going to measure metallicities of high redshift galaxies? James Webb is going to provide measurements of rest optical emission lines that we often use to measure metallicities at lower redshifts out to redshift 6, 9, even 12 for some line ratios of O2 and neon 3. But how can we turn these measurements into metallicities that are accurate, unbiased, and have precision to do the science that we'd like to do? So at lower redshifts, the way we typically do this is through the use of what we call strong line calibrations, where we have calibrations that relate metallicity to ratios of strong, bright optical emission lines like the O3 over N2 ratio that I've shown in these plots here. These calibrations can be either empirically calibrated to small samples that have an independent measurement of metallicity through what we call the direct method, or theoretical calibrations from photoionization models. And it's a really great method because you can use lines that are easy to detect. And James Webb will detect a lot of these bright emission lines from many sources in the epoch of reionization. But the issue here is that for either of these cases, the properties of your calibration sample, whether that sample be photoionization models or whether that sample be actual observed galaxies in H2 regions, have to match the properties of the sample that you're determining the metallicities for. And the issue we have here is that, of course, there have been no observational constraints on metallicity at redshift greater than 6 yet from emission lines. We just don't have the observations. And for the theoretical side, we don't know the ISM conditions at redshift greater than 6 that we should use as input to the photoionization models. We have guesses, but they're ultimately only guesses until we get strong observational constraints. And so what we need to do is figure out how we're going to establish the relationships that we'll use to measure metallicity from the line ratios that JWST is going to provide for us. Now, just quickly to mention, why should we expect that the situation is different at redshift 6 than at low redshift to begin with? And in particular, we see already at redshift 2, we see that there's evolution in the ISM conditions as evidenced by the offset of the BPT diagram between low and high redshift star-forming galaxies. And then at redshift 2, we can even start to measure these direct method oxygen abundances, these direct method metallicities. And we already see offsets from redshift 0 calibration. So we already see evolution of redshift 2. We expect that the evolution will be, if anything, even larger once we reach redshift 6, 7, 8 in the epoch of reionization. So as a solution, we'd like to get these direct method metallicity measurements in the epoch of reionization to establish the metallicity scale and be able to get accurate metallicities to interpret all of these science cases. So the direct method metallicity I've been talking about, this requires a few ingredients. You need to understand the electron temperature and the electron density of the gas in H2 regions. Then you need to have measurements of lines of hydrogen Balmer lines, and then also oxygen 3 and oxygen 2 to measure the doubly and singly ionized oxygen populations. And we get these from optical emission lines, the O2 and O3 and H beta lines from strong lines. We can get the density from doublets like oxygen 2 or sulfur 2. And then we get the temperature usually from optical auroral emission lines like oxygen 3 4363. This is a very weak line, but it's very sensitive to the gas temperature. Now, if we want to do this at redshift 6, we can get the strong optical lines with James Webb in a few to several hours per target. And so that's very reasonable. But this oxygen 3 4363 line and other auroral emission lines are so weak, they're 50 to 100 times weaker than the strong lines, that we need something like 50 to 100 hours or more per source to detect this line in the epoch of reionization. And that's obviously completely unfeasible. So we can't do that. So what I'm going to talk to you about today is actually an alternative method to get direct method metallicities, where instead of relying on the optical auroral emission lines, we're going to be using the far infrared oxygen 3 lines at 52 and 88 microns, where you can also determine the temperature by taking a ratio to the oxygen 3 5007 strong line in the optical. And so with this setup, this basically shows you we can get the temperature from the far infrared oxygen 3 lines. We can get the electron density from the ratio of the 52 to 88 micron far infrared line. You can also get this from the O2 or sulfur 2 doublet, but those trace the lower ionization outer regions of the H2 regions, whereas the oxygen 3 is in the inner regions. And so it's actually better to get the density from the oxygen 3 lines themselves. And then, of course, you can still get the strong lines from JWST to get these direct method metallicities. And in particular, just to make a note on why oxygen 3 52 microns can be so useful, is compared to the 88 microns, the metallicities derived based on temperatures from the 52 micron line are much less sensitive to changes in density, as long as the densities are below, say, a couple of thousand, as we see at lower redshifts. And might be the case at redshift 6, although we don't know yet. The 88 micron line is actually very sensitive to the density. And I just wanted to shout out, tomorrow we're gonna have a theory talk from Shengqi Yang, who's going to be talking about an analytic theory approach to these far IR O3 lines. So make sure to tune in for that as well. So this ideal situation to get these direct method metallicities from the combination of ALMA and James Webb observations is really great, but we don't have James Webb yet. And we've actually never detected this 52 micron line for Epoch reionization sources, just because it basically hasn't been targeted for a lot of objects yet. And so what can we do? What can we learn about galaxy metallicities now before we have these new observations? So basically what we have now, we don't have the optical lines from James Webb, and we don't have the 52 micron line. We have detections of the 88 micron line for several redshift greater than 6 sources from ALMA. And then we also have HST and Spitzer photometry where we can learn about the galaxy SEDs. And so basically what we've done is made several fiducial assumptions about the temperature and the density, and also about the oxygen 3 to oxygen 2 ratio for an ionization correction. You can infer the H beta luminosity from the star formation rate based on SED fitting, and then we can use the oxygen 3 88 micron line, and we can combine all these pieces together to get direct method metallicities that obviously rely on a lot of assumptions, but are at least a great first stab at what the galaxy metallicities are of these UV bright targets in the epoch of reionization. And so basically you get this expression that combines the 88 micron luminosity with the star formation rate from the SED, where you can determine the metallicity.
2 minutes left.
Perfect. Now, there are a lot of systematic uncertainties because of our assumptions. They total to about 0.4 dex, so a factor of about 2.5 in systematic uncertainty on the metallicity. But the great thing here is that if we have the rest optical lines from James Webb, and if you add the 52 micron line from future ALMA observations, if you detect all these lines at roughly 5 sigma, then you basically reach 0.1 dex precision in the metallicities, which is competitive with the best that we can do in the local universe. And you eliminate all sources of systematic biases. So it's really an amazing observational approach to get great robust metallicities in the epoch of reionization. Just to briefly mention, we've tested this 88 micron method with our whole host of assumptions on local objects, local dwarfs that have measurements of this from Herschel. There's a great one-to-one correspondence, so we think it works quite well. And just to show some science results here in the last minute, this is basically the mass metallicity relation, so metallicity versus stellar mass in red for objects at redshift 7 and 9 with the 88 micron line detections. And these are the metallicities that we've inferred for them. The star shows the average of this sample of 5 UV bright sources. We find that the average metallicity is something about 10 to 20% solar metallicity. So these things certainly are not extremely low metallicity. They're moderate metallicity. This has some interesting implications for the stellar metallicities based on the expected alpha enhancement we think are in these objects. And so it suggests that these objects harbor iron poor stars that are highly efficient producers of ionizing photons. That's important for their ability to reionize the universe. We see an evolution towards lower metallicity that's basically consistent with what's seen extrapolated from studies at redshift 2 and 3. And then these metallicities of 10 to 20% solar imply that there's at least 100 to a few hundred megayears of constant star formation in the star formation histories of these galaxies. And so it implies that the Balmer break is actually going to be a significant contributor to the Spitzer IRAC excesses in these redshift greater than 7 sources. And that star formation first began in these galaxies at a redshift of greater than 10 for most of these sources. So just to wrap up, ALMA plus JWST is the only viable path forward to metallicity calibrations, the epoch reionization, which are going to be extremely important because for the very faint galaxies that we think powered reionization, and also for the galaxies at the highest redshifts, redshift greater than 9, 10, JWST is powerful, but it's still only going to measure a few bright emission lines. And so we really need to establish these calibrations to be able to turn those few bright emission lines into physical properties that we can connect to all of the other observables we have for these sources. So I'll stop there. Thank you for listening.
Well, thanks, Ryan, for such a great talk. We have time for a very short question because we are a bit delayed today. from Matus Rybak. Are we hoping to pick up the auroral lines in the strongly lensed sources? This might reduce the JWST time required by 1-2 decks.
Yes, yeah, I think that's a very exciting prospect, and it definitely might be possible, but I think the highly magnified sources for which you'll be able to do that will still be very few, and so you might be limited to only a few or a handful of sources. And really, we'd like to get to statistical samples of say a few dozen, where you can actually start to try to piece together calibrations. But if we can get those observations, they'll still be very valuable for understanding the ISM conditions of these galaxies. So I definitely think that's something we should try for.
Well, thank you very much. You have more questions, but you can continue the discussion by the Slack chat. So thank you again. Well, very nice results. This was our last session today. We thank very much all our speakers, and well, you can continue the discussion in Slack. We kindly ask the speaker to be around in the Slack to take questions and continue the discussion. I don't know if Peter, Aswin, or Chris would like to say something before we leave.
I think I'll just like to say thanks to everyone, and I'm looking forward for another session tomorrow. I think it's great, and I think it works very well, and I think the SOC did an excellent job on keeping the time together with the speakers. Thanks.
Yes, many thanks to all of you for attending our first conference day. And well, we invite you to join us tomorrow.
And yeah, so we'll take a group picture tomorrow, right? Tomorrow after the session. Because people are starting to log off now. So bye, everyone.
Bye, bye.
And thanks to, especially to Ilsang Yun for asking so many excellent questions.
Yes.
I see there are still many participants around. I guess these are the people that just logged in and then left.
Yes. I think that perhaps as we can stop recording, I don't know if
yes, definitely.
Okay. I don't know if the recording continues